let's talk about integration and polar coordinates. So polar coordinates is very similar to rectangular coordinates, the xy coordinate system that we have been using since calculus 1. Polar coordinates is another way to describe the position of a point on a two-dimensional plane. Okay, so for polar coordinates, we will need two pieces of information, r and theta. If I have a point here on the plane, r refers to the distance from the point to the origin. Theta will represent the angle from the positive x-axis to the line segment connecting the origin and the point. Okay, so let me give you an example here. I have a point that has xy coordinates 1, 1. So 1 unit along the x coordinate and 1 unit along y coordinate. If you compute this, you will find the distance from this point to the origin being square root 2. Okay, and the angle from the positive x-axis to this line segment being pi over 4 or 45 degrees. So under the polar coordinates, I will say, oh, the polar coordinates for this point is r theta equal to root 2 and pi over 4, versus this is how you write it using the rectangular coordinates or Cartesian coordinates. Okay, and these two coordinate systems are related through these equations. So the x coordinate equals the radius r times cosine theta, and the y equals r sine theta. So in this example, if you compute root 2 times cosine of pi over 4, you will find that this is equal to 1. So that is the x coordinate. And similarly, if you do r times sine of theta, you again find the y coordinate, and this is equal to 1, like by actual computation. So root 2 times 1 over root 2, that is the value for cosine pi over 4. So this cross out, and that equals 1. So similarly for the y coordinate. Okay, so this is how we know if we have something that is described using xy coordinates. We can always use these equations to write the x and y in terms of r and theta. Okay, so these are important formulas. And remember that we talk about the double integral. So if I have a region and a function, then I can say I want to integrate this function over the region R. So this is a double integral. It gives you the volume of the solid under the surface. It's equal to F over the region R. Okay, so if I give you a little sketch, so this is the region R, and F looks like this over R, so this is Z equal to F of XY. So I have a surface. Okay, then when I compute the double integral, integrating F over the region R, what I get would be the volume of this is solid. So this whole thing under the surface. Okay, then this is hard to compute because by definition it requires taking the limit of the Riemann sum, and that is complicated. So we have Fubini's theorem that tells us if you can describe the region R using inequalities of x and y, then you can find the value through iterated integrals. So we can do dx dy. Okay, so g1 of y, g2 of y, a to b. For example, this is just an example, okay? And so in here we see that under rectangular coordinates, dA, the area is basically the base times the height, right? So this leads to the formula dA equals dx and dy, okay? And when using polar coordinate system, we are dividing the plane in a different way. So it'll go like this. So different angle theta will go like this. Different radius r gives you circles like that. So you can see that the division, the partition under the polar coordinates is different. So in this case, when I want to do Fubini's theorem under polar coordinates, x, according to the formula, becomes r cosine theta, y becomes r sine theta, and the dA, the area now, is r dr d theta. Oops, not giving enough space. Let me do this again. So f of r cosine theta, that's the x value, r sine theta, that's the y value. Then I have r dr d theta, that is equivalent to dA. Okay, so that's the formula that we have. The area element now being converted to r times dr times d theta. So you have to pay attention that we have this additional r, okay? And the range of r will go from, let's say, like h1 of theta to h2 of theta, and theta go from angle alpha to angle beta. Okay, so this is just a abstract example. I'm gonna give you a concrete example, but just keep in mind the relationship between the rectangular coordinates and the polar coordinates is this two equations. That's how you convert, how you write x and y in terms of r and theta. And this is how you derive the area element dA in terms of iterated integral using the polar coordinates. So it's r dr d theta as opposed to just a dr d theta. Okay, so that's the difference when you use the polar coordinates and the rectangular coordinates.